Hi, Johnny Hancock here. Oscilloscopes are usually the go-to instrument that engineers use to begin testing electronic designs. Testing often requires high-resolution measurements to verify low-level analog signals such as power supply output ripple, as well as low-level analog signals from the output of sensors. In this short demonstration, I'd like to begin by showing you why the number of bits of conversion are important for accurate, low-level analog signal measurements. But perhaps more important, I'll show you why using a scope with a high sensitivity, low noise front end can enable you to see signal details that are often lost in the noise floor of other scopes. I'll be demonstrating these measurements on the HD3 oscilloscope, which provides 14 bits of analog to digital conversion. I'll be sharing additional specifications of this scope near the end of this demonstration. Let's get started. When engineers refer to an oscilloscope's measurement resolution, they are usually talking about the number of bits of conversion of the scope's analog to digital converter, or ADC. Not too many years ago, 8 bits was considered the industry standard. 8 bits of conversion provides 2 to the 8th power, or 256 unique levels of conversion across the dynamic range of the analog to digital converter of the oscilloscope. Each additional bit doubles the number of levels of conversion. So 9 bits provides 512 levels, 10 bits 1024 levels, and so on. The HD3 scope provides 14 bits of analog to digital conversion. This provides over 16,000 levels of conversion. So, why is this important? Most engineers would probably say because they don't want to see a stair-step or jagged waveforms due to a limited number of bits of conversion. In other words, they want to see a smooth waveform. Let's see an example. This is a 500 millivolt peak-to-peak 200 megahertz sine wave from a low-noise signal generator. The scope is set at 100 millivolts per division. At this setting, the HD3 with 14 bits of ADC resolution provides approximately 100 microvolts of measurement resolution and shows a smooth waveform trace. Another reason why most engineers want a scope with more bits of resolution is because they don't want to see a fuzzy waveform, or waveforms that aren't thin and crisp like I just demonstrated. But truth be told, the fuzziness of waveforms that you might be familiar with is not typically due to a limited number of bits of conversion. It's usually due to the noise floor of the scope itself. What you might be seeing is random noise introduced by the oscilloscope itself, not due to a limited number of bits in the ADC. This phenomenon can usually be observed on the scope's more sensitive volts per division ranges, such as 5 millivolts per division or below. Let's now see an example of a fuzzy waveform on a scope that has lots of bits of conversion. This is now a 5 millivolt peak-to-peak 200 megahertz signal with the scope set at 1 millivolt per division. Between 500 microvolts per division and 2 millivolts per division, this scope provides 2 microvolts of ADC resolution. At this low setting, you can probably see some fuzziness to this waveform, but this is the industry best for this class of scope at such a low volts per division setting. The HD3 oscilloscope has a baseline noise level of less than 50 microvolts RMS at the scope's full 1 gigahertz bandwidth. Oscilloscope vertical resolution is not just a function of the number of bits of the ADC. It's a combination of the ADC bits plus the noise floor of the scope, which comes into play when viewing low-level signals at very low volts per division settings on the scope. So how can we improve baseline noise level of the oscilloscope to make higher resolution measurements at these more sensitive volts per division settings? One method is to use waveform averaging. This requires the input signal be repetitive. As you see here, when I select averaging, now it's thin and crisp. Another method is to decrease the bandwidth of the oscilloscope, which naturally reduces the noise level of the oscilloscope. Here you can see what this 200 megahertz sine wave looks like if I reduce the system bandwidth from the full 1 gigahertz down to 350 megahertz. Now you have less noise, less fuzziness, and now we're down to a baseline noise level of approximately 30 microvolts RMS. This is now a 20 megahertz sine wave at full bandwidth, 1 gigahertz. I'm going to reduce the bandwidth to 100 megahertz. And now the noise floor is significantly reduced, and we have a thin and crisp waveform at such a low volts per division, 1 millivolt per division. Sometimes using a lower bandwidth oscilloscope is a benefit. The HD3 oscilloscope allows you to select the bandwidth of your oscilloscope measurements anywhere from 5 megahertz all the way up to the full 1 gigahertz bandwidth of the scope, which lets you lower the noise floor of the scope down to as low as 10 microvolts RMS at the lowest bandwidth settings, giving you the flexibility to trade off bandwidth and noise for any application. Thanks for watching this demonstration of the HD3 oscilloscope. The HD3 oscilloscope comes in bandwidth models ranging from 200 megahertz up to 1 gigahertz. This scope samples at a maximum rate of 3.2 gigasamples per second across all channels simultaneously, along with 100 megapoints of acquisition memory for each of the 4 analog channels. Perhaps the most important attribute of this oscilloscope is its 14-bit analog to digital conversion, along with a low noise floor at under 50 microvolts RMS, even at full 1 gigahertz bandwidth. This oscilloscope also supports a wide range of advanced analysis features, including zone trigger, pass-fail mask testing, and a broad range of serial bus decode and triggering capabilities. For more information about the HD3 oscilloscope, visit the URL listed on your screen. Thank you.